What is the universe made of? The universe, in all its grandeur and mystery, is composed of a remarkable tapestry of matter, energy, and forces woven together across the deepest stretches of space and time. To uncover the answer to the question of what the universe is made of, we must embark on a journey through both the vastest expanses of galaxies and the most minute subatomic particles, linking together the knowledge of ancient philosophers and modern-day physicists. Let's begin with what we can see and touch, ordinary or baryonic matter. This is the stuff that seems familiar, the kind of matter that makes up our everyday lives, our planet, the sun, and the luminous galaxies that sparkle like fireworks across the night sky. Ordinary matter consists of atoms, themselves made of protons and neutrons in the nucleus, orbited by electrons. All the chemical elements on the periodic table, hydrogen, helium, oxygen, carbon, iron, gold, are made of these fundamental particles arranged in myriad combinations. The stars get their fuel from the nuclear fusion of hydrogen and helium, the two lightest and most abundant elements in the universe. As stars evolve and eventually die, especially in explosive supernova, they forge the heavier elements, carbon, oxygen, silicon, and iron, necessary for planets and life as we know it. Remarkably, only about 5% of the cosmos is composed of this familiar material. When scientists peer into the deep recesses of space, they find glaring discrepancies between what they observe and what theoretical models predict. Something unseen must be at work, a shadowy presence exerting its influence on galaxies and the universe as a whole. This leads us to the profound and enigmatic concepts of dark matter and dark energy. First, consider dark matter. Its existence is inferred from observations such as the rotation speeds of galaxies. If galaxies were made only of the visible matter we can see through telescopes, they would spin so rapidly that their stars and gas clouds would fling away into space. But something invisible appears to provide additional gravity, holding them together. Dark matter does not emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects. Dark matter makes up about 27% of the universe. That means the vast majority of the universe's matter is actually this invisible, mysterious substance. But as perplexing as dark matter is, an even greater mystery dominates the composition of the universe: dark energy. In the late 1990s, astronomers tracking supernova explosions in distant galaxies made a stunning discovery. The expansion of the universe is not slowing down, as once thought, but accelerating. This acceleration requires a repulsive force, a kind of cosmic anti-gravity, working in opposition to gravity. This force is attributed to dark energy. Dark energy is even more enigmatic and less understood than dark matter. While its effects are observed on the largest scales, pressing the galaxies apart, its true nature remains a subject of intense debate and investigation. Some theories suggest it is a property of empty space itself, arising naturally from the mathematics of quantum physics, a cosmological constant, first introduced and later abandoned by Albert Einstein. Astonishingly, dark energy constitutes about 68% of the universe. Simple arithmetic shows that nearly everything we understand and can interact with, planets, stars, gas clouds, interstellar dust, accounts for only a minuscule portion of the cosmos. The majority is dark, mysterious, and only dimly glimpsed through its gravitational or expansive effects. To sum up what the universe is made of, approximately 5% ordinary matter, 27% dark matter, and 68% dark energy. Yet even within this 5% of ordinary matter, not all of it gathers into stars and planets. Much remains as vast clouds of gas and dust and diffuse plasma found between galaxies. At a larger scale, galaxies, massive gravitationally bound systems of stars, gas, dust, and dark matter, form some of the grandest structures in the cosmos. Galaxies group themselves into clusters, which gather further into superclusters, all interconnected in a vast cosmic web. Amid all this ordinary matter and its formations, dark matter is woven, acting as the invisible glue of the universe. Without it, galaxies would never have come together. The clusters of galaxies would fly apart, and the universe's structure would be unrecognizable. Despite being invisible, dark matter can be mapped. Astronomers use techniques such as gravitational lensing, the bending of light by gravity, to see where dark matter exerts its effects. When light from distant galaxies passes through regions rich in dark matter, it bends, creating distinctive arc-shaped images. Yet our understanding of dark matter is incomplete. It interacts very weakly, if at all, with ordinary matter except via gravity. Satellite-based detectors buried deep underground have been constructed in hopes of spotting one of these elusive particles as it passes through the Earth. Additionally, the universe is filled with electromagnetic radiation, light in all its forms, from gamma rays to radio waves. The cosmic microwave background, a faint afterglow of the Big Bang, is perhaps the most significant of these radiations. It pervades all space, carrying with it information about the universe's birth and its evolution over billions of years. Cosmic rays, powerful particles moving near the speed of light, incessantly bombard Earth from deep space. Magnetic fields, woven through galaxies and clusters, add another layer to the intricate cosmic fabric. Beyond the physical components, the universe is structured by four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Gravity binds planets, stars, and galaxies on the grandest scales. Electromagnetism governs the interactions between charged particles, defining chemistry, biology, and even our technology. The strong nuclear force holds atomic nuclei together, while the weak nuclear force drives certain kinds of radioactive decay, essential in the chain of reactions powering stars. All known particles and forces, except for gravity, are described by the so-called Standard Model of Particle Physics, an extraordinarily successful theory developed during the 20th century. Yet gravity itself, described separately by Einstein's theory of general relativity, remains somewhat apart from this quantum picture, a hint that our deepest understanding of what the universe is made of may still elude us. In pondering what the universe is made of, we must also recognize the timescales involved. The universe began some 13.8 billion years ago with the Big Bang, a sudden eruption of energy and then matter. In the earliest moments, only the simplest particles could exist. Within minutes, protons and neutrons formed, later combining into the first atomic nuclei. Hundreds of thousands of years later, atoms formed, and the universe became transparent, releasing the cosmic microwave background radiation. As time passed, gravity drew gas into clumps, forming stars and galaxies. Through nuclear fusion in stars and explosive stellar deaths, the universe became richer in elements. Planets, life, and ultimately intelligence could emerge. Thus, the makeup of the universe is a dynamic story, changing through eras, from a searing plasma of particles to a universe of stars and galaxies to an ever-accelerating realm governed by dark energy. Eventually, the fate of the universe may be determined by its ingredients. Will it keep expanding forever, cool and empty, or face dramatic transformations in the distant future? Looking further ahead, the universe's ultimate destiny might lie in what it is made of. If dark energy remains dominant, space will expand at an ever-increasing pace, leading perhaps to a big freeze, where galaxies grow so distant and the energy so diffused that stars exhaust their fuel and darkness prevails. But these speculations underscore the profundity of the question: what is the universe made of? The answer, as we now know, is multi-layered, a combination of the ordinary and extraordinary, the visible and invisible, the well-understood and the thoroughly mysterious. Scientists probe deeper each year, smashing particles together in accelerators, surveying distant galaxies with telescopes, tracking the subtle whispers of neutrinos and gravitational waves. Each discovery brings new understanding and often new puzzles. The search is not only for the ingredients, but for the recipe, how these components interact, combine, and evolve to create everything from the simplest atom to consciousness itself. The universe is a construction of structures within structures, from the quarks and leptons that make up protons, neutrons, and electrons, to atoms, molecules, stars, galaxies, and the enormous cosmic web. Overlaying all is the gravitational force of dark matter and the expansive push of dark energy. Even our questions are shaped by the universe's makeup. Why is the universe composed mostly of matter, instead of an equal mix of matter and antimatter? Why did the Big Bang produce the precise mixture it did? Are the laws and particles we know truly fundamental, or are there deeper layers waiting to be discovered? The journey to answer what the universe is made of is far from over. Each new discovery brings with it avenues for wonder, unsettling our understanding, and beckoning us deeper into the cosmic mystery. For now, we celebrate the knowledge that we are part of an intricate, interconnected universe, Born from stardust, governed by forces both familiar and strange, our existence a fleeting spark in a cosmos whose true nature may forever invite awe, curiosity, and exploration.